Người là tập điều hết这个是吧？那后面有一个人在等后面，那个人叫那个孩子，
Ciao, young fan.
Hey, good bro.
Yeah.
Okay, group number 5. Group number 5. Siapa group number 5?
Group number 5, Doctor.
Group number 5. Share slide. Group number 5, share slide. CC, share slide.
Okay, Doctor.
Okay. Silakan.
So, can we start now?
Ya, 15 minit je. Jangan lama sangat. Laju sikit. Jangan baca slide. Elaborate.
Okay, good evening to Dr. FUA'AD. So we are from group 5. So today we are going to discuss on the control system design assignment. So next. So this is the content on, this is the content that we are going to discuss.
Group members tengok.
Group members, so they are Chao Xiangfeng, me, and Yong Di Wei on group 5.
Okay.
So first of all, this is our question 1. So basically, we are going to use the bot plot method to design a phase-led compensator where the requirement is on the settling time to a unit step of 2 seconds, and also percent overshoot of PO, which is less than and also equals to the 10%. And also we have to simulate the closed loop system with a step input of 10 degrees per second, and also show the time history of
on video. Group 5 on video. Video on. Continue.
So this is our flow chart on how we solve on the question 1. So first of all, we start, then we look on the requirement, and also we do the observation on the question. Then we start on doing the manual calculation by using the bot plot method, and also we do the Matlab verification on our calculation. So then we check on our answer when the requirement is met. Then we had solved our question 1. So if it's not, then we will look back and also do again on the manual calculation by using the bot plot method. So this is our flow chart. So this transfer function that we got from the question. So, and then we had the specification on the setting time, which is less than and equal to the 2 seconds and 10% of overshoot. So this is the bot plot that we use the Excel to plot. So then we had found out that the gain margin is 2 dB at the frequency of 3.5 radian per second. Then next, and also the phase margin at 5 degrees at frequency of 3 radian per second. So from the previous slide, the time response slide, sorry, next. So
Where is the time
Sorry,
response?
a bit lag of the.
Lag, ah.
Yeah.
Kenapa? Slow kan?
Yeah.
Ni UTM ni line ke?
Yeah.
yeah, very slow.
Can we show it like this?
You jangan pakai slideshow, you pakai non slideshow. Gitu saja, gerak-gerak gitu ni. Sebab
Okay.
hari hujan line slow.
Okay, then this is our uncompensated time response. Then we found out that the settling time is at 182 seconds and overshoot percentage is around 113. So the next slide. So these two is the specification that we need to improve. So we design the lead compensator. So our requirement is 10% of overshoot. So by using these two standard graph, we can find out that the requirement phase margin is the 60 degrees. So next, so by using the phase margin of 60 degrees and we use the correction factor where equals to 5, then we found out that our phase margin maximum is 60. Then from here we can find our beta, which is equals to 0.0718, and also our magnitude at 11.4 dB. So from the previous bot plot, then we can find out by this negative 11.4 dB, we can find our maximum frequency at 5.7 radian per second. So from here, then we can find our ZC and also the PC. Then here we can generate our lead compensator function, which is the 13.9 in bracket of S plus 1.527 divided by the S plus 21.27. Then the last transfer function here, then we got our compensated open loop transfer function, which is this equation. So next. So then we did on the Matlab verification. So this is the uncompensated bot plot diagram by using the Matlab. So here we can find out that the phase margin is around 3.79 degrees here, so which is around similar to our answer that we found on manual, which is the 5 degrees. So next. So this is the compensated bot plot that we did. So then here we found out that our phase margin is 40.7, so which is our requirement is not met, where the requirement is around 60 degrees. So next. So also we are still doing the same step by using different correction factor like 10, 20, 25, and 30. But then we still cannot got the phase margin around 60 degrees.
Why?
Not sure.
Not sure.
But then we come up
design. Okay. Teruskan.
Yeah. So next. So this is the method that we did where we did the gain adjustment. So because of our phase margin is 40.7 degrees, so which is not enough, then we apply the gain adjustment. Then we change our gain, and also we found out that the best gain is at around 6. So then we use this our lead compensator transfer function. Then we also plot on the Excel. Then we can find out that our phase margin next is met on our requirement, so which is around the 60 degrees. So then, yeah. So also we also check on the compensated time response, and also we had met the requirement where our settling time is around 1.41 seconds, and also our overshoot percentage is 6.63, which is lower than the requirement. So that's our solution. So this next, this is our Matlab source code where we do the verification, also the plotting on the Excel. So
what do you mean by log space? What do you mean by log space here?
log space here is the
Anybody can help?
The log space is actually the point, the frequency range lah. That means is F mean is the 10 power. That means 10 power F mean and 10 power F max is the range.
Okay.
F mean is the lowest and F max is the highest. That means 10 power F max and 10 power F mean. So here the F mean is -1. That means 10 power -1. So the lowest is 0.1.
Then 1000?
That means 1000 of data. 1000 data.
Data.
10%.
Okay. Okay, Louis, continue.
okay. So that's all for the method
That's
one.
all.
Then
Okay.
pass to Chao Xiang Feng.
One last question
Pass to Yong Yu.
to Louis Shishi.
Yes.
What is the difference between lead and lag compensator? 3 differences.
Lead and
Number
lag.
1, E number.
The
Number 1.
The lag compensator is used to improve the transient response by adjusting the phase margin.
Lead compensator.
Yes, the lead compensator. Then the lag compensator is to improve the steady state
Okay,
error.
number 1, correct. Number 2.
The lag compensator is to increase the steady state error by increase the low frequency gain. So we are adjusting the gain.
Somebody help? Yong?
For the lead, the PC is greater than ZC.
Okay.
For the lag, the ZC is greater than PC.
Okay,
Must be.
number 2. Number 3. Chao Xiang Feng. Tak dengar lah, you cakap.
Dengar sekarang. Okay.
Dengar.
Okay, the lag computer, we use the lagging in the phase shift, whereas the lead compensator we introducing the phase shift, the leading phase shift. So there is the difference.
Faham ke? You orang tak faham.
Yeah,
Yang
the
mudah,
system is
yang mudah pakai beta lah. Beta equal to ZC over PC less than 1 for lead compensator. Beta is greater than 1 for lag compensator. The ratio between ZC over PC. Okay, next. Sambung.
So I will continue to present the next part. So actually we have used another method to solve the problem, which is cascaded lead compensator. That means we use 2 lead compensator to solve. And we use the first compensator is using the correction factor for 5. So the phase margin now is 40.7. That means the measure phase margin is 40.7. So we do the same step, but the only difference is the initial margin is 40.7. And then we use the first correction factor is 10. Then we found out that the second lead compensator transfer function is 2.92 times and times S plus 4.85 and over S plus 14.4 14, 14. Then this is the final GC is a transfer function with two lead compensator. Then after that, without that, for the correction factor 10, the phase margin is 55.4, which is not enough also. Then we increase the correction factor to 20, is 59.4. Then it's still a little bit smaller than 60, then we use 22, which is the previous one, and is 60. So for the second compensator, the transfer function is 4.88 times S plus 4.35 over S plus 21.22. And this is the final compensator open loop transfer function. And here is the Matlab code same as the previous one. Only the function is different. This one is have two lead compensator function.
Okay.
And
excuse me.
yes.
What do you mean by squeeze?
Squeeze.
Squeeze.
Actually, from the data is actually presented for the Hirsch magnitude. It's actually presented in 3 dimensions. Then we use squeeze to cut it to 2 dimensions.
Tak faham.
Tak faham.
Apa tu? UCC, explain lah. Squeeze apa? Macam saya ingat squeeze ni macam buah limau. The squeeze dapat air, dia punya air. Apa maksud squeeze, Chow Jiang Feng? Dia punya mikrofon
Dia
rosak.
decrease, please. Can hear? Dia decrease the dimension lah, like the way mentioned just now. Decrease by 1.
Yeah, if A is like 1, 2, 3, 4, and another A is 2, 3, 4, 5, then we cut, we make it become 1, 2, 3, 4, 2, 3, 4, 5, like this. That means you combine them.
Apa maksud awak cakap macam mana ni? Tak faham. Awak ada 3 kolom data.
Yeah. 3 dimension.
3 dimension? What do you mean by 3 dimension? Macam ini ke? X, Y, Z?
Yeah.
Okay. So?
That means for the data, the Z, it has A1, A2, A3, A4.
Okay.
Then we just make it become X and Y.
Oh, okay.
Okay.
I got it.
Okay. This is the after cascaded lead compensator plot. And to check the phase margin, we need to find when the gain is 0 dB. So at this 0 dB, the omega is 9.66. So we find the 9.66 at the phase. That means the omega PM is 9.66. Then from here, the 9.66 is actually negative 120. That means the phase margin is 60 lah. Negative 110 plus 180. Then this is the time response. The settling time is 0.62, and for the overshoot is actually 10.969 minus 9.84 over 9.84 is around 8%, the overshoot. Okay, so for the discussion question 1, we have found that by inserting the lead compensator, we can reduce the overshoot to 6.63, and the settling time reduced to 1.41. And for the cascaded, it also can reduce the overshoot to 8.52, and the TS reduced to 0.62.
Right.
And both of them have the get the specification. The time, the TS less than 2 and the OS less than 10%. But we think the first method is more preferable because cascaded lead compensator might have might be more expensive because it need more component to achieve the cascaded lead compensator. Okay,
next.
That's all for my part.
Continue, next.
So I will continue the question 2. Okay, so the picture show is the question 2. Okay, next. Okay, this is basically our flowchart like mentioned by Shishi just now. The only difference is that only the third step with which is the calculation using the root locus method. In this question, we're going to use this method in order to solve our question. So next. So based on the question, the requirement is the steady state must be lesser than 10% for a step unit input. So it should be lesser than 0.1. And also the phase margin must be greater or equal to 45 degrees. Setting time lesser or equal to 5 seconds for a unit step input. And also the most important is the root locus method, because this question asks us to use this method. Okay, so next. So we also use the Matlab. So before we insert the lag compensator, so this is the frequency magnitude. We export the data from Matlab to Excel and plot using the Excel. So this one is the frequency magnitude, and this one is the frequency phase response. So basically, there are two phase margin. Based on our research, we found out that we should use the closer one, which means we have to choose the value, the phase shift value is closer to next 180 lah. Okay, so next. So this is the time response before we insert the lag setter. So the ES now is 0.67, as we know the final value from this plotting is around 0.33. So we use the as a unit step. So 1 minus 0.33, and we get the ESS is equal to 0.67. And also the set time from this plotting is 2.46 seconds. So next. So this is we use the margin function in Matlab, and we get the same result as we observe from the plot. Okay, next. So from the time response, we found that TS is equal to 2.46, which is acceptable in our question, but the ESS is 0.667, so we need to do some improvement in order to reduce it. So
wrong spelling.
Next.
Wrong spelling.
Wrong spelling.
Response S.
Okay. S. Okay. Sorry for that. So we decided to use a lag setter in order to improve our ESS. So since our ESS must be lesser or equal to 0. So we choose a value for it. So we make it 0.0. Then from the transfer function, we know that the system is type 0, as it has no pulse at origin. So we use KP. So next. So from the research from internet, so in this question, it mentioned that we have to use the root locus method. So we find some information from the net. So this is the manual calculation. So at first, we didn't determine the T final first. So we based on the ESS, the formula. So we get the KP final equal to 11.5, and also the initial value. We use the ES in order to find these two different values. Okay, next. So after that, we use the formula in order to achieve the final value. So we have to another gain, which also mean the lag compensator. So in this case, we use the ratio method mentioned by the information by internet. So we, after calculation, we got the ratio from to P is equal to 23. So then we choose two values for the pole and 0. So we choose 1 for 0, and the pulse is 0.5. After that, we get the transfer function for our compensator is equal to that I show it below that 11.5 x plus 1 over x plus 0. Then later we make cascaded, then we final transfer function. Next.
Okay.
So this is our MATLAB source code for before the lag compensator. So the first part is how we create the transfer function, and the second part is how do the pop plot, and the third part is how we generate a time response, and the last part is how we use the margin function. Because the margin function is also mentioned by the question, we have to use it. So after that, we export all the data into the Excel and do the plotting.
Okay.
So, okay, then this goes with the after we adding the lag compensators, just the same. Okay, so next. So after we add the lag compensator, this one is the frequency managed response, and when we found that the frequency is around 15 when the the gain margin is the magnitude is around 0D. Okay, so next.
Okay.
And if we found that the phase shift is around -117 is around -120, so around our phase margin is around 60. Okay, next. So this one is the time response after we adding the lag compensator, and it shows that our ESS now is improved, which is now is 1 minus 0.9, which equal to 0.08, which is match our desired output.
Okay.
So the settling time also improved.
Okay.
So this is a result. We use the margin function. Okay, next. So after designing a lag compensator using the root rocker method, we use it into our system, and we found the ESS range from 0.667 to 0.08, which is improvement for our system. And also the TS reduced from 2.4 seconds to 1.45 seconds because the ratio we do a little bit of gain adjustment, so affect the transient response. Okay. So the phase margin reduced from 90 to 60. Okay, so all match our elements. Okay, so
Next
I want to make some. I want to make some conclusion. Okay, so in conclusion, we successfully design and apply a lead compensator in question and achieve our requirement, and also we successfully design and apply a lag compensator using root rocker method in order to achieve our. So lastly, manage. Okay.
Okay. Thank you. So overall, very good. Very good slide. Very good very satisfactory presentations. Congratulations. Okay. No corrections. Acceptable as status quo. So thank you very much. You can exit the Zoom, and we invite next group number 4. Group number 5 can exit.
Okay, thank you both.
Sudah habis. Louis Cici sudah habis. Boleh tidur.
Okay.
谢谢你。
谢谢 Doktor.
谢谢，不要客气。Group number 4. Group number 4. Hello. Tak ada orang?
Hello, sir.
Ada orang tak?
Ada, sir.
Semua dah ada on video. Members group, tunjuk members. Members.
Teguh Syariman, Fazli,
Jap,
and
jap. Fazli.
Ya, saya doktor.
Wan Hazrul.
saya Doktor.
Present cepat sikit, laju. Jangan baca. Laju. Start.
Okay, I will present the first question. This is the question, and for the manual calculation is we use Excel, and we got the 9.88% overshoot, and 60% face margin. And for the Matlab simulation, this is the coding for the question 1. So this is the open loop transfer function, and this is a closed loop. And this column is to see the phase margin from the board plot, and the second column is to see the percent overshoot from the step function. And this line specifically to see the step info, to see the overshoot. This is a function to see the overshoot from the step function graph. And okay, this is our board plot. From our board plot, we get the again 0.036. Then we calculate the no. I mean, from the board plot, we can see that our phase margin is 60. Because 60 plus 100 minus 120 plus 180 is 60. So we got the phase margin 60, and for the percent overshoot, this is our step function, step response. I mean, this is our step response, and the percent overshoot is 8.7726, which is meet the criteria from the question, which is 8.8. So next is question 2. Will be presented by and this is our observation, findings, suggestion, improvement, idea. And next is Shahiman will be presenting question 2.
Silakan.
Yes, thank you, Fazli. For the question 2, this is the question. So from the question, we have to search for the K and using the phase margin 40 degree. Okay, next. Okay, and this is the flowchart and the manual calculation. So using the question asked for the 40 degree phase margin, and we search for the X is X equal to positive 180 equal to 40. So S equal to negative 40. So using the board plot, next slide, using the board plot and next slide, other next slide. Okay, using the board plot, we can see that the phase margin is 100 negative 140 and the frequency is 11.7, and at the magnitude graph, we can see that the magnitude is negative 15.6 at the frequency 11.7. Back. Okay, back. Okay, using the gain, we can search for the K1, and using the formula 20 log K1 equal to gain, we can say that K1 equal to 6.03, and to search for the K, we have to use the 24.2 because from the question we got 24.2 and multiply with K 6.03 and we will get the K. Okay. And this is the Matlab simulation for the what we call it for this graph, and the K is equal to 6.03, which we calculate that, and that is the open and closed loop, and this is the graph that we got after we plot the after we put the k, the new value k, and we can see here that the phase is negative 140, which is the phase margin is 40 degree. So it's meet the requirement for the question. That is 40 degree. Okay. Next. So this is the observation that we serve, and we successfully get the acceptable potential controller. Phase margin is 40 degree, and yeah, mostly we managed to follow the question and get the same result that the question wants. That's all from me. And the question 3, Wan Hazrul Hazim, please.
Yeah, thank you, Kushaiman. Okay, for question 3, this question is ask us to find the compensator GC so that the steady state tracking error is 0, and also the settling time is within the 2% criterion, which is TS less than or equals to 5 seconds. So next. So for the calculation, since we don't have much more detailed information, so we just use assumptions. So for we first determine the desired closed loop location for desired settling time. So our settling time is less than 5. So we assume as the dominant point is TS equal to 4. So the pole location is S equal to -4. And then next we design the compensator, which is we use the PID compensator, which is integrator compensator at S equal to -4. So so K equal to Ki over S. So we will get Ki over S plus 4. And then we will analyze the closed loop system. So so we will get TS equal to Ki over S, S plus 2, and S plus 4. And then we will determine the value Ki. So we assume the Ki is 100 because we want to get the 0 error steady state. Since we when we increase the gain, the steady state error will be decreased also. So next. So this is the Matlab code for the original transfer function. So G equal to 1 over S multiplied by S plus 2. Next.
SISO tool tu apa?
Oh, SISO tool is actually it's a tool to get all kind of graph which is transfer function, root locus, state response, and boot plot.
SISO tu apa?
SISO.
SISO. SISO tu apa?
SISO.
Herman.
I don't remember.
SISO. Kau panggil SISO Kita panggil
Ya.
Fazli. SISO apa?
Sistem input, sistem output.
Salah. Syahirman.
Sorry, Doctor, I don't remember.
Single input, single output. Bukan.
Apa dia? Single input, single output. Betul? Single input. Okay, teruskan.
Next. So this is the original root locus. Next.
Sekejap. Fazli.
Ya, Doktor.
Ni garisan apa?
Yang mana? Itu. Frekuensi. Sekejap.
Tak tahu.
Frekuensi, sekejap.
Syahirman, ni garisan apa?
Apa nama dia?
Oh, apa nama dia? Ini tak datang juga ni. Awan Hazrul, ni garisan apa?
Natural frequency.
Natural frequency, betul. Omega N. Fazli, ni garisan apa? Fazli,
Dem natural frequency.
damn natural frequency. Astaghfirullahaladzim.
Sekejap.
Bosak budak-budak ni. Syahirman, ni garisan apa? Lagi satu
Frequency.
tak tahu. Wan Hazrul, ni garisan apa?
Damping ratio.
Damping ratio. Nampak damping ratio ni? 0.16 ni damping ratio ni. Kan? Apa
Ya.
you buat ni? Fazli. Fazli, ni paksi apa?
Pasti imaginary.
Engineering.
Ah,
Engineering. Berapa zeta dia?
Zeta dia.
Hmm.
Itu 1.
1. Astaghfirullahaladzim.
Eh.
Syahirman, zeta dia berapa?
0.
0.
0. Fazli, awak banyak tak faham Kelas dulu
Terlupa.
Ni zeta dia berapa?
Itu 1.
1.
Itu under damn legend.
Ini yang basic aku tak tahu macam mana nak exam dah ni. Sambung.
Next. So this is the step response for the original transfer function. So we can see the settling time is over 5 seconds, which is 5.83 seconds. So we need to adjust the settling time first. So next. So this is the new code for the new transfer function. So we use the integral compensator, which is k equal to 100 divided by s plus 4. And then multiply with the original transfer function, we get this. And then next. So this is the new root locus. Next. So the set response, we can find that the setting time is adjust to less than 5 because of the s plus 4.
Laju.
Okay, next. So from this question, we can see that the setting time is below 5 seconds, and also the steady state is 0. So for the improvement, I think we need to practice more in using Matlab. So that's all from us. Thank you.
Saya tak nampak Excel file dengan Simulink, saya tak nampak.
Saya dah hantar email baru, tapi kami boleh dapat buat yang question 1 je. Question 2 nanti tak tahu macam nak buat.
Tak tahu macam mana nak buat. Awak hantar pukul apa awak hantar bila lambat
baru je.
Yelah, you hantar assignment bila? Hari Isnin
kami macam lambat 20 minit.
Lambat 20 minit hari Ahad?
Ya, hari yang lepas due waktu due tu.
20 minit lama tu. So tak ada Excel dan tak ada Simulink. Okay. So, kalau nak improve, boleh improve hari Sabtu hantar. Okay, terima kasih banyak-banyak.
Thank you, Doctor.
Thank you,
Doctor.
Group number 3. Group number 3.
Yes.
Bun.
Yes.
Isaac and
Isaac
and Wei
Lee.
Ho.
Yes.
Let me write your names first in the marks. Bun, Isaac dengan Lee Wei Ho.
Yeah.
Pasal muka tak sama
Gambar lama.
Oh, gambar lama. Ayah. Gambar lama. Spek pun tak sama. Start.
Okay, so we are from group 3. We are doing for assignment question 3. Okay, this is our question. Our question, there are 3 cases of the controller, which is proportional controller, integral controller, and proportional integral controller. So for these 3 cases, we are going to design for these specs, settling time under 10 seconds and percentage overshoot under 10%. So next, okay, the flow chart is we are given the specs, so we find the zeta from the percent overshoot from the standard graph, and then use Matlab to find the dominant poles, and then we get a gain from the root locus plot. Okay, for these 3, and then compare all of the controller. Next. Okay, this is how we find the zeta by calculation, or we can get it from the standard graph. Next. Okay, for zeta equals to 0.6. This is our Matlab code for this graph, and then we use cursor to find the dominant pole, which is negative 2.5 plus 3.35 J, and then the percent overshoot from this root locus plot is 9.58, and then the gain is 11.5. Next, this is for the proportional controller, the same procedure, and then we find the dominant pole. We get a gain 4.37 and percentage overshoot 9.51. Next, this is for the last case. Same procedure, get a gain 9.7 and then percentage overshoot 9.54. Next, please. Okay, this is the plot we plot from the Excel. Okay, next. Okay, this is the comparison between 3 controller. For the proportional controller, we get the gain 11.5 dominant poles and then percent overshoot. This is the data gathered from previous 3 root locus plot. Next, the settling time of each of the case we have calculated 1.6 second, 6.13 second, and 1.9 second, which is under the specification, which is less than 10 seconds. Next. Okay, we put all the step response together and then compare. Can have the detailed comparison in the next page. Next. Okay, next. Okay. Yes, this one. Okay. So for the proportional controller, we have steady state error with 0.343. For integral controller, steady state error 0.01. PI controller, steady state 0.062. And then settling time, we have higher settling time on the integral controller. And then the percent overshoot, 9 point something, which is all under the specification. So yes, the discussion, we can see from the comparison between the 3 controller, which you can refer to the previous table, and then from the integral controller and the PI controller have low steady state error, but the integral controller have the highest settling time. So in conclusion, we use a PI controller is more suitable because it gives less steady state error and a lower settling time.
Where is the graph?
Oh,
yeah, okay.
Yes. This one is from the Matlab, and then the previous one is from the Excel.
How you import the data from Matlab to Excel?
Right matrix.
Right.
We save all the data in T1 data, and then write all the data into Excel file.
Automatic, when you run this, it will open the Excel.
Yes. Yes. Yes.
Oh, no need to open Excel, dia automatic baca daripada sini
This one is we write the data into the Excel file. Yes.
Oh,
We
Excel
run the
file, okay. Nanti dia keluar macam sebelah kanan tu lah.
Yes.
Oh, lepas tu plot je lah macam biasa.
Yes, correct.
Oh, bagus, bagus.
All right, I think this is for question 1. So
Okay,
we'll pass
next.
to second question.
Okay, Doctor, good evening. So I'm going to present the second question. So the second question is just basically we have a PD controller and a spacecraft model. So basically this question wants us just to find the root locus and then the value of the KD over KJ, KP over KJ, and we should make sure that the settling time should be less than 4 seconds lah, and the peak overshoot also should be less than 10. Okay, so the flow chart is almost the same, which is we find the zeta and then derive the formula. Then we use Matlab, and then we just drag the cursor to find the dominant pole. And then we can also use Matlab to find the settling time, and then to check whether it fulfilled the condition of the given question. And then at the end, we can find the unknown, which is represented by K. Okay, so zeta calculation is the same as the question just now. It's just basically plug in the formula. So we get 0.6. And then given the question is, they give us the spacecraft system is 1/j². So we just plug in the PD controller formula, which is the KP plus KD over KDS. And then we just create the open loop transfer function. Then we get this formula. And then we just swap and swap the variable and we get this. So after we get the equation, we just put into Matlab, same thing, S equal transfer function S, then plot that we can see the dominant pole is negative 3.58 plus 4.78 I, and then the damping is 0.6, which is close to the value just now. And the overshoot is 9.51, which means that we reach the targeted, which is less than 10% overshoot. Okay, next. Okay, so we also use Matlab the same way also. So we import data from Matlab into Excel using Red Matrix.
Question?
Yes.
How you import the data from Matlab to locus to Excel? Because the data have two parts, real part and imaginary part. How you differentiate?
How? Is we declare the real is equals to we transpose the data.
Okay.
So real, because we already set the G4 data as the root locus. So we create another variable called real, and then we transpose it, and then we capture the real data from G4 and then imaginary also we create another variable that we capture again.
Mr. Lee, Mr. Lee, what is transpose? Mr. Lee, lazy dia pula. Saya tengok badminton dia tengok panggil lazy dia. Mr. Lee, what is transpose? Is it transpose or what? Courier ke apa? Transpose.
Transpose actually is a mathematical, how to say?
Say lah. How to say lah. Something.
How to say?
Tanya Bun lah. Bun dah tahu dah tu. Nak tanya you je. I bagi tips interchange.
Interchange the row and the column.
Pandai. Interchange between the row and column lah. Jadi sekarang ni I set existing dia punya matrix dia tu column ke row? Before transpose.
Existing.
Before transpose dia punya vector tu column ke row?
Oh, that one.
I say tak faham. I say kan matrix kan dia ada column row.
Okay.
Baris dengan lajur. Tak tahu nak cakap Cina tak pandai. Saya bahasa Inggeris lah. Column and row. Column ini macam. Sekejap saya notate sikit. Column ini macam. Column.
Okay.
Row ini macam. Ni row mah. So kalau dia ada dua kan. Ini. Macam ini kan. Kan matrix kan dia ada macam ini kan.
Yes.
Kalau dia transpose so dia jadi macam ini mah. Kan?
Yes, right.
Kan? Tu saya tanya, before transpose, dia punya real tu column ke vector? Column vector ke row vector? Tanya Bun
It should
tahu.
be originally horizontal lah, one row.
Tanya Bun, before transpose, the column vector tu is a column vector ke atau row vector?
Column vector.
Kalau column vector macam ini.
Row. Oh,
Column vector macam ini.
Yeah, row.
Ni column vector. Kalau row vector dia macam ni. Data dia. Macam tu. Bun, before transpose, data tu row vector ke column vector?
Row vector.
Row vector.
Yes.
Row vector. Jadi you transpose row vector tu menjadi column vector.
Yes. So that so that we can have a clear table in
jadi macam inilah
Excel.
Kuasa T. Ini kena faham ni, data ni. Kita ni electrical electronics, kita banyak data tapi tak tahu nak analisis. Itu yang susah.
Okay.
Mr. Lee, boleh faham ke? Okay, continue. Bagus, bagus. I learned something from you.
Okay. Okay, so this one already experienced. Okay, so now we just determine the settling time from the dominant pole we obtain. We just basically plug in 4 over real, which is 4 over this, and then we get the TS. Yeah, and then we plot using Excel, so we get the same graph.
That's why I ask the student to use Excel so that they learn how to, import, export data. Nampak tak dia punya purpose dia?
Yes.
Lagipun Excel dia punya grafik sangat cantik. Matlab tak berapa cantik. You see? Tengok dia punya graph cantik. Okay, continue.
Okay, thank you.
Okay, good evening, Prof. Now I'm going to say the final question. So in this question, actually is more simpler than the previous question. We only need to plot the root locus for the K, and then the zeta is already given. So a flowchart, we just use the Matlab to find the dominant pole using the zeta given. Then we just determine the value of K for the pole, dominant pole. So this is the coding. And then for the damping, 0.707 is okay. Then we get the overshoot is 4.28. The gain is 9.13. So the K is 9.13. So the question is only like this. So this is the Excel of the root locus. It look like this. Then end of the question. So for conclusion, we can say that the PI controller is the best controller among the others.
Okay.
Yeah, among the two others controller due to it has the lowest steady state and shorter settling time. And then the zeta is very important to find the dominant pole. And we need to use it to find the K and also determine the system whether it's fulfilled the settling time or not.
All right.
So this is our reference, and thank you.
Okay.
This is all from our group.
Okay, very good slide. Very satisfactory presentation. So I hope you learned something from the assignment, even though it's 15%. Okay, but the emphasis is on the coding lah and data transfer. Soalan senang je kalau buat manual, tapi kita nak tengok dia punya skill, cakap, tak gigil, kan? Ada confidence. Lah to take you time pukul 9.
It's okay.
Kelas, besok kelas. Sekarang dah rehat, tunggu test tu pun sudah siap tanda. Besok lusa saya letak di luar, ambil sendiri.
Okay.
Dapat 40. I think about 30% of the class dapat 40 per 40.
Oh.
So maknanya saya punya effort and my approach is ada menampakkan hasil lah.
Yes.
Tak
Yes,
faham.
betul. Very nice.
Yes.
Jangan lupa isi itu EPP.
PPPP.
Okay.
Jangan
Full marks, full marks.
kalau tak dapat full mark, jangan emosi. Isi itu EPP. Mau tenang-tenang, lepas makan, relax-relax, baru isi. Okay, thank you. Session ini.
Alright. Thank you, thank you.
Right.
Okay, group number 1, please. Chow Jiang Feng, boleh keluar mah? Group number 1.
Where ada teh?
Oi, jauhnya. Kau kat mana ni?
Assalamualaikum.
Group number 1 ni hantar lambat.
Assalamualaikum and good evening.
Group number
So
1 hantar lambat ke?
from belum present. Sorry.
Group number 1 ni hantar lambat.
Mana dulu?
Hantar assignment lambat.
Okay.
Hello.
Keluar.
Orang tanya ni. Hello. Hello.
Hello teh, hello.
Group number 1 hantar assignment bila? Lambat Hari Senin
Hari Isnin.
Lambat. Due date 18, kau hantar 19
Atas 19 tu.
Lambat lah.
Terlambat.
Sambung. Dah lah, hantar lambat. Present pun paling lambat. Astagfirullah. Tajuk sikit. Jangan baca.
Okay, boleh Dato'.
Baca tolak markah. Elaborate.
Okay, baik. So we are from group 1. Here is our members. My name is Amirul Hazi Amrin, the most handsome one. And our leader Muhammad Iqbal Ihsan bin ADMA. Di muka. And the last one, Syed Muhammad Harishah bin Wan Rahman. So for the first question, Syed.
Laju.
Okay, so for the first question, the given the transfer function, so GS equal 25 over S cubic plus 10 square, 10 S square plus 40S plus 25. Then for B equation is S plus 10 over S square plus 2S plus 10. And then for C equation, GS equal to S square plus 2S plus 4. Then followed by the equation and then no need to read lah. Okay. So next slide. So this is the instruction or the code for the first question. So then beside the code is the board plot for the first question, 7.1a. So the coding is a simple coding. First we declare the numbers and the denominators, and then we generate the transfer function. And then we generate the root locus plot. So next slide, please. So this is for the B, 7.1D, same as the first question, 7.1A. Then next. So also this is same as the others. C question C, 7.1C. Then next is 7.1B. Okay, so next. So the previous one is the solution by using the Matlab code, and then this one is the solution by using a manual calculation. So for the first one, the given transfer function. So first we find the open loop poles and then open loop zeros by using the factorization or using a calculator. Then from that we get the closed loop transfer function by using the formula GS over 1 plus GS. Then we get the closed loop transfer function and then the characteristic equation. Then we generate a root width table, which is RH table. And then from them, we get the range of the stability. And then here is the plot manually. We use sketch. So next question for 7.1b. Also the same as previous one, which is 7.1a. We find the open loop zero, but here we do some different, which is we find the break-in point since the plot is causing the gradient axis, I guess. Okay. So from them, we find the K value by using the formula K. Then the K value is equal to 36.87. Okay, so for C question. So C question is same as the B question. So here we can obtain that the type of the system is type 1.
Laju sikit, Syed.
Okay. Okay, so open loop poles and then open loop zeros, and then we find the breaking point, and then the bottom at the right bottom is the sketch for the, what you call it, apa ni? Apa lupa saya. For sketch for the transfer function. Yeah. Next. Okay, this is same as the previous one. Also, here is the open loop poles and then open loop zeros. There is a lot. Okay, that's all. Next, I give to, here is the flow chart. For the all four questions for 7.1, A, B, C, and D are using the same flow chart. So here is the flow chart. First, we write the transfer function in Matlab file, then run the M file, and then obtain the root locus by using the rlocus instruction. Then we find and filter, breaking point, away, the imaginary closing, and by using manual calculation, then we sketch it manually, and then compare it to the Matlab plot similar with the manual sketch or not. Okay, next. So here is the discussion. So I think that's all from me. Next, I give to Amirul.
Okay, so for my part is question CP 7.2. First, we obtain the value of K using rlog find in Matlab to find the value of K. And then we proceed to calculation, manual calculation to compare. We obtain OL zeros and OL poles by closed loop transfer function. And then we obtain characteristic equation by open loop transfer function. By RH table, we need to find the value of K, which is K critical that we obtain here is 0.79. Then we sketch root locus that we need to find. So here is a flowchart for question 2. Same like question 1. We find first using Matlab, find K critical using rlog find. And then we compare. If there is error, we repeat the same question. So here is discussion about question 2. which our finding for question 2 is if K exceed K critical, which is 0.79, the system become unstable. So our suggestion, the exact of K value can be found from manual calculation from H table. Improvement that we can do is make sure all root of the system not lie on right half plane. Last improvement that we can do is to make, if we want to make the system stable, the design must take into account that it is constantly in underdamped region. So that's all from my part. Next, Iqbal.
Okay, Assalamualaikum. Okay, so for 7.4, the question is the given negative feedback system for the transfer function, and the question is to develop an M5 to obtain the root locus as P various, which is P is more than 0 and less than infinity. For what values of P is the closed loop stable? Next. Okay, so this is the Matlab simulation. So next. Okay, so for the calculation part, so firstly, the given for the negative feedback, so we transfer it, we take the characteristic equation. So we do some mathematical equation so that we can get the open loop closed loop transfer function, which is gs is equal to s minus 1 multiplied with p and divide with s square plus 5s plus 10. Okay, and then from that we take the characteristic equation to identify the value of gain. Sorry, there.
Characteristic equation.
Characteristic, yes. Okay, so by using the
laju sikit.
Okay, okay, Prof. Okay, so we obtain that the value of gain, value of P is less than 10. So range of the stability is P is less than 10 and more than 0. Okay, this is the flowchart that we use to identify the answer for 7.4. Okay, so for the discussion part, what we observe is the stability, the range of stability is K less than 10 and K more than 0. And what we finding is we use the RH table to identify the range of stability for P. And the our suggestion is the plot all zeros and poles need to connected at the left plane to ensure the system is stable. And the improvement is we avoid from the over amplification, introducing gains restriction. Okay, so for the last question is we need to determine the characteristic equation, and then we need to using RH creation to determine the value of K and to develop M5 to plot the root locus and compare the result. Okay, next. Okay, so basically the for the A, this is what we done, but we not sure.
Macam mana dapat 6 dengan Dan tu?
From the XT, from the metric.
Tengok mana metriknya.
Dekat calculation.
Mana dia? Oh, calculation. Oh.
From the calculation.
Oh, okay. Conversion. Pakai conversion. Okay.
Oh, okay. Okay, so
dia asing kan, lepas tu tak nampak. Oh, asing kan, dia tak nampak. Okay lah, terus.
Oh, okay.
Excel tak ada
Apa dia, Prof?
Excel tak ada.
Tak ada, Prof.
Simulink tak ada.
Simulink pun tak ada.
Astagfirullah. Itu format lah. Dia kendaki.
Discussion.
Teruskan. Okay, discussion. Okay lah ni. Faham lah ni, saya faham. Okay, conclusion.
Okay, so for the conclusion, for the frequency analysis, we actually for the stability, we know that the value of stability is from the left half plane. So for each point on the root locus will be determined by the limiting value of the gain system. And then from the characteristic equation from the closed loop transfer function, we will get the possible value of the maximum K.
Yeah.
I think I make it short, so this is the conclusion from us.
Alright. So, tak ada Excel, tak ada Simulink dan tak nak tambah apa-apa biarkan saja. Kalau nak tambah Simulink dengan Excel boleh buat hari Sabtu atau.
Prof, actually I have a question about the Simulink. I have no idea what should we put in the Simulink.
Okay, tengok dia punya soalan. Soalan ni. Tengok soalan. Sekejap. Tengok Ini nak roll locus kan? Second question. Second question. Sekejap. Local find the value. Okay. System stable. Okay. And show the wrong. Okay. Jadi masukkan K sama dengan 0.79 ke dalam. Dia cari close loop. Kemudian buat time response. Buat dia punya block diagram. KGS tu. Masukkan K 0.79. Masukkan numerator, denominator tu. Dalam kotak Simulink tu. Kemudian buat unity feedback. Kemudian inject step. Tengok respon dia. Stabil ke tak stabil. Kamu kena kreatif lah sikit. Ini macam apa orang kata tu kejong aja macam ikut je tak pandai nak elaborate ke apa. Macam mana saya nak komen sekejap. Saya nak annotate. Semua nak kena tunjuk. Tak boleh berfikir langsung budak-budak ni. Saya nak annotate Tadi saya boleh conteng. Sekejap. Option ya. Left side. Saya tak boleh conteng Tadi boleh conteng. Tahu tak?
Tak keluar. Kenapa tak boleh conteng?
Tadi saya boleh conteng. Ya.
Ada.
Tak boleh conteng lah. Stop participant sharing. Tak boleh bawa sharing kan. Tengoklah Simulink. Awak type dekat Google YouTube.
Okay, boleh.
How to get time response from Simulink. Simple je. Macam unity feedback. Lepas tu kamu run, letakkan oscilloscope dekat input dengan output. Satu wire bagi input, satu wire bagi output.
So kita akan observe dekat OSI.
Senang je, tak susah.
Okay, boleh.
Kalau tak boleh nanti WhatsApp lah. Okay. Teruskan.
Okay, terus.
Yang ini dia memang tu obtain the root locus tapi varies. Kalau root locus memang tak ada lah dalam Simulink. Cuma satu je lah yang tadi tu. Nak tengok dia stabil tak stabil. Lagi 7.4 tak payah. Tak payah simulink. Yang ini determine the characteristic equation using the value of K. System stable. So, dapatkan nilai K tu. Masukkan dalam transfer function tu. Tengok dia punya time response. Close loop. Bila nak tengok time response bukan open loop. Mesti close loop. Tengok dia punya time response. Stabil tak stabil. Sebab dia bila perkataan stabil tu kita nak tengok time response dia. Kalau time response dia membesar, oscillate towards infinity, itu maknanya tak stabil. Kalau dia oscillate constant, dia marginal stable. Kalau dia membesar tanpa had, dia tak stabil. Okay?
Boleh.
Kalau nak baiki, boleh baiki. Hari Sabtu hantar. Itu sahaja yang saya boleh tolong. Sekian, terima kasih. Dah malam.
Terima kasih, Prof.
Thank you, Prof.
Assalamualaikum.
Terima kasih, Prof.
Assalamualaikum.